So in this video, we're going to get into some of the applications of the derivative. And so the rest of the chapter 5, we're starting chapter 5 today. And chapter 5 is mostly about what can you do with a derivative. So we've kind of been looking at different types of functions. How can you find the derivative? And now we're going to start looking at what's the use of this? What can we do with the derivative? And many different things. So hopefully you're very adept at finding derivatives because pretty much every problem in this chapter, the first step is to find the derivative of the function, and then we're going to do things after that. So if you're not good at finding the derivatives, that's something that's probably step one that you need to take care of as we move forward. So this first part of this section is a little bit of a review from algebra. These will be these topics you've seen before, and then after we reintroduce these topics, we will get into the calculus of it. So increasing and decreasing functions. This is something that kind of naively you probably understand, and you may have seen the definition before, but just very naively thinking about this, if we have a graph, as we move from left to right, if the graph is going up, then it's an increasing function. If it's going down, then it's a decreasing function. And so we always say, even don't worry about this arrow that looks like it's pointing up. So we see that arrow pointing up, you might think that's increasing, but we are really only concerned with as we move from left to right. So as we move in this direction, what is the function doing? And if we're moving in this direction, this function is decreasing, and again decreasing, whereas this function, even though we have this arrow here that's pointing down, it's just telling it that we're going to keep, it follows this pattern. That's really all that's used for. It's not talking about the direction of the function. So we always move from left to right when we are talking about increasing or decreasing. Is a function increasing or decreasing? So let's look at a more mathematical definition. So if we have a function defined on some interval, then for any two numbers, and we'll just pick a couple of numbers. Let's say x1 is 2 and x2 is 5. F is increasing on the interval if f of 2 is less than f of 5, and we can see what that means. So if we have a graph, there's 2, there's 5. So if f of 2 is less than 5, let's say f of 2 is there, and f of 5 would have to be up here. So f of 5 is greater than f of 2, and you can see it however you want to connect this. It doesn't really matter how you connect it. But for any two numbers in this interval, if f of x1 is less than f of x2, then we're increasing. And then if f of x1 is greater than f of x2, we're decreasing. So that's a mathematical definition. It's perfectly fine to just think of it as when we look at the graph, is it going down from left to right, or is it going up from left to right? And here's a picture. We can just look at this function, see if it's increasing or decreasing. So we'll have kind of two rows here. So we'll have increasing row, we'll have decreasing row. And so let's just start on the left. As we start on the left, we are moving down until we get to x equals -1. So all of these intervals where we are talking about if the function is increasing or decreasing, these intervals are always talking and listing x values. And so we don't really list x values, but we write them in intervals. The other thing to notice is we always put parentheses at the endpoints. Obviously, infinity always has parentheses, but even the numbers, the finite numbers, when we're talking about increasing and decreasing, will have parentheses. So we don't use brackets on these. So once we get to -1, then we are increasing until we get to the top here. So right there, we are at the top. That looks like it's at 2. So between -1 In 2, we are increasing. And then we start decreasing until we get to 4. So we're going to use a union. Between 2 and 4, we are decreasing. And then after 4, we are increasing. So this will be union 4 to infinity. And that's all. Of course, this is algebra. Probably something you saw when you took that class in pre-calculus as well. That's mostly of a recap. We might see a couple of warm-up problems on the homework, but not really what we're interested in for this course so much as how do we use calculus to tell where a function is increasing or decreasing. So the great thing about calculus is things like this. We're talking about graphs, but you don't really need the graph. So if we know some calculus that we're going to learn here, we can tell if a function is increasing or decreasing by looking at the derivative. So just to recap and remind ourselves, the derivative of a function is talking about the instantaneous rate of change. Or another way to think about it, it is the slope of tangent line. So when we have a graph, and hopefully we know this, but just as a reminder, when we have a graph, if we're talking about the derivative, we pick any point on this graph, we can find the tangent line. The slope of the tangent line is the derivative. So we'll just say f prime, let's just say that's c, so f prime of c would be the slope of this tangent line. So the test here, test where f is increasing or decreasing. If the derivative is positive, then f is increasing on that interval. And so if you think about, so let's just say we have this function here. This one would be increasing from negative infinity up to this point. And if you think about the tangent line at any point, the tangent line will always have a positive slope. And that corresponds as well to the derivative, because the derivative is the slope of the tangent line. So if the derivative is positive, that tells us that the slope of the tangent line is positive, which tells us that the function is increasing. And then likewise, if the derivative is negative, then the function is decreasing. So if the derivative is positive, function is increasing. If the derivative is negative, function is decreasing. And then if the derivative is 0 on an interval, then the function is constant. And so when we say constant, of course, we are talking about a section where the line is horizontal, or the function is horizontal. And then that would mean that the slope is 0, which means the derivative is 0. So in these cases, we don't need the graph. We can look at the derivative. We don't need the graph to find the derivative. We just need the function. And so that can be very helpful. Here's a couple of terms that we're going to see a lot in this chapter. Critical numbers. So critical numbers are anywhere that the derivative equals 0 or where the derivative does not exist. And then the critical point is the ordered pair of the critical number. So the ordered pair, so if c is a critical number, that means that the f prime of c is 0, and the critical point would be c f of c. So whatever the value of the function is. So when we talk about points, we are talking about ordered pairs. If we're just talking about numbers, it's just a number, a single number usually. All right, so let's see an example, and we can see how does this work in practice. So we have this function, and we want to find where it's increasing or decreasing. So step 1, and this will be step 1 on almost every problem that we do. Step 1, take the derivative, or find the derivative. Probably find the derivative is a better way to say it, but find the derivative f prime of x. So this is where hopefully you're very good at finding derivatives now. This is a pretty easy one. Polynomials are pretty easy to find. So negative 3x squared minus 4x plus 15. Step 2, set f prime of x equals 0 and solve for x. And what does this give us? This gives us our critical numbers. So let's set this equal to 0. We will, I'll switch the signs. We'll divide by -1. So that first term is positive. Usually that's a little bit easier to work with. And I believe, I think this comes to x plus 3, and then that would be 3x minus 5. I looked at this beforehand. I think that works. So we have 9x minus 5x. That works. Okay. So our critical numbers, critical values, are -3 and 5/3. Okay, so these are the critical numbers, critical values. So what does that mean? That means that at these points, the slope of the tangent line is 0. And only at those points is the slope of the tangent line 0. So what that tells us, because we know the domain of a polynomial is all real numbers, so every other number at every other point on this function, the function is either increasing or decreasing. So we have 2 points where the tangent line is horizontal. So the tangent line will be horizontal there. Everywhere else, tangent line will be either positive or have positive or negative slope, which means the derivative will be positive or negative. So now once we have these, test intervals, we'll see what this means. Test intervals for increasing or decreasing. And so all we need to do, we know that at these 2 points, the tangent line has a 0 slope. Every other point, the tangent line would have to have a positive or negative slope. And if the tangent line has a positive slope, the function is increasing. If it has a negative slope, the function is decreasing. So the way we're going to do this, let's set up a number line. And let's put these 2 numbers on our number line. So -3 and 5/3. Obviously, you want to put them in order. And so we can pick any number. So we know that f prime of -3 is 0. We know that f prime of 5/3 is 0. Now, any other number will have either positive or negative. So let's pick any number over here. So pick any number less than -3. So let's say -4. So let's pick x equals -4. You can pick -5, you can pick -6, you can pick -100. Doesn't really matter. But let's pick f or x equals -4. Now we're going to plug this in to the derivative, and we're going to see if this is positive or negative. So here's our derivative up here. -3 times -4 squared minus 4 times -4 plus 15. And let's see what that gets us. So we have -3 times 16 plus 16 plus 15, and that gives us -17. That is less than 0, so that is a decreasing interval. So we know that, let's start a couple of rows over here. So we know that the derivative is negative. That tells us that the function is decreasing. So from -infinity to -3, we are decreasing. All right, now let's pick a number in this interval. So the easy one to pick would be 0. So any number between -3 and 5/3 will work. 0 is an easy one, so let's pick 0. So x equals 0. Let's find f prime of 0. So we'll plug that in up here, and we'll write it all out because this one's a pretty easy one. So f prime of 0 will be 15. That is greater than 0. So that tells us we are increasing. So between -3 and 5/3, we are increasing. So -3 to 5/3, we are increasing. And now let's look at any number that's greater than 5/3. So you can pick any number, doesn't matter what it is. Don't pick 5/3 because we know that f prime of 5/3 is 0. Pick any number greater. So you just pick the easy one, pick 2. But you can pick anything. So f prime of 2, we have -3 times 2 squared minus 4 times 2 plus 15, and that will be, let's see, -12 minus 8 plus 15, we get -5. Now, it doesn't really matter what the value is. If you can tell that this is going to be negative, you don't really need the number necessarily, unless the homework specifically asks for it. But if it's just asking it increasing or decreasing, we really just care if this is positive or negative. Same thing with these two. Um, so this one is negative, so that tells us that it is decreasing. So I could have put a positive here, increasing, negative here, decreasing. So we're decreasing from negative infinity to negative 3 and from 5/3 to infinity. And then we're increasing between negative 3 and 5/3. All right, so now this one says to graph, and you might think that's how am I supposed to graph a cubic function without a calculator? Well, you can actually do this pretty easily. Because we know where it's increasing and decreasing. Now all we need to do is find the values of the critical, like find the function values at the critical points. So let's find f of negative 3. So this is, now we're looking at the function. So I'll write this in just so we're clear we're using the function, not the derivative. Squared plus 15 times negative 3 plus 10. And let's see what we get. Negative 3 cubed minus 2 times negative 3 squared plus 15 times negative 3 plus 10. And I get an error. Helps if you do this correctly in the calculator. Negative 26. Negative 26. So we need to plot the ordered pair negative 3, negative 26. So negative 3 will be approximate here. Negative 3, negative 26, about there. Then let's get the other. I mean, these are going to be our turning points. So you can see kind of the picture of the graph. The graph is going to come down like this till we get to x equals negative 3. Then it's going to come up till we get to x equals 5/3, and it's going to turn again. So these are our turning points. So now f of 5/3, I won't write out everything, but we're plugging in 5/3 into the original function. And let's see, 2 times 5/3 squared plus 15 times 5/3 plus 10. And we get, well, it's 24.8. So this is not going to be extremely perfect. It's not going to be perfect at all. About 5/3, somewhere between 1 and 2, more than 1.5. And then we get to 24.8. So we'll say about right there. All right. And then we know it's going to, I mean, it's just more, make it a little bit more accurate. We know it's going to cross the y-axis at 10. So we plug in 0 for x, we get the y-intercept is 10. You could also find the x-intercepts if you want. Might not be super easy with this one, and it's not super important. We're getting an approximate graph here. So we know it's decreasing till we get to here. We know it's going to increase till we get to here. And then it's going to decrease. And so that is what our function looks like. And if you want to check it, you're welcome to check it. This is not perfect, but it is very close. And that's the main thing, especially for a polynomial. That's really all you need. You need where is the derivative 0, and where is it increasing, where is it decreasing, and then you can get a good picture of this polynomial. All right, so let's look at a couple more. Let's look at x minus 1 to the 2/3. Now, probably you don't know what this graph looks like. But we can still find where it's increasing or decreasing. So the first step, of course, take the derivative. And the derivative of this will be 2/3 x minus 1 to the negative 1/3. Then we want to set it equal to 0. Now you might want to put this as a positive exponent. So let's make it 2 over 3 cube root of x minus 1. All right, so now where does this equal 0? This will never equal 0 because in order for it to equal 0, the numerator has to equal 0. So no solution to this. Okay. No solution to this, but the derivative does not exist at x equals 1 because that does not, that's not in the domain of this. So the derivative does not exist there. So critical number is x equals 1. So now let's test our point. Let's test our interval. So now we need to pick any number that is less than 1. Plug it into the derivative. So let's test 0. Well, I need to write that, but let's test 0. So now f prime of 0 will be 2 over 3 cube root of negative 1. So cube root of negative 1 is negative 1. So this will be negative 2/3. 2/3 less than 0. So we are decreasing. This is negative. We are decreasing in that interval. And then let's pick a number greater than 1. We can pick 2. F prime of 2, we get 2 over 3 cube root of 2 minus 1, which would be 1. That gives us 2/3. That is greater than 0, so we are positive, which means we are increasing. So we are increasing from 1 to infinity. We are decreasing from negative infinity to 1. And if you want to check this graph, I think it looks something like this, where this is 1. So when x equals 1, the function is 0. So it does come down. And if you wanted to see if you want to see what happens as we are coming down, the slope is getting steeper and steeper. And if you think about why that is, if you plug in numbers that are closer and closer to negative 1, or closer and closer to 1, this is getting closer and closer to 0. So we have 2 over a very, very small number, which is going, small negative number, in fact, which is going to negative infinity. So the slope is getting steeper and steeper, but it stops at that point. And then as soon as you get past 1, all of a sudden it gets very, very steep in the positive direction. And so we have this cusp right here. So we call that a cusp, where you have a kind of it's not exactly a corner. It's kind of a cinched in corner, I guess you could say. All right, so let's look at one more. Steps are the same. We're going to find where this is increasing and decreasing. So step 1, take the derivative. So we need our quotient rule. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So we get x plus 1 minus x plus 1. And so that gives us 2 over x plus 1 squared. And so next thing would be to set this equal to 0, but we also actually know this will never equal 0 because this can never be, actually the numerator can never be 0. That's what we need. When this is negative 1, so it's never equal to 0. In fact, it is always positive except x cannot be negative 1. So x equals negative 1 is the only critical number. And then everywhere else it's positive, so we actually don't even have to really test anything because 2 is a positive, of course. X plus 1 squared is always positive, so this will always be positive. So this is actually increasing everywhere. And I believe, if I remember right, you can check me on this, but this function will have an vertical asymptote at negative 1 and a horizontal asymptote at 1. Take the limit to infinity. And so I believe we're increasing the whole time, so I believe this graph looks something like this. think that's what it looks like. Now, we don't have to draw it. You don't have to draw these most of the time. They have you draw the polynomial, but the polynomials are usually easy to draw. We don't have to draw this, but you can check this, um, and you can kind of deduce what this will look like. And we will eventually get to where we're going to be drawing these. And so you're going to use, besides the derivative where it's increasing and decreasing, we're going to see how we know that it takes this shape versus a different shape. We're going to see, obviously, from algebra, we know how to find asymptotes. And so different things like this. So we're eventually going to get to where we can draw almost any fairly basic function. It won't be anything super complex, although you probably could draw, you will eventually get to where you can draw complex functions. It's just maybe you just manually doing it takes too long. It's not really worth it, or too tedious or whatever. But you will be able to do this where you can draw this graph eventually. But in any case, this first section about increasing and decreasing. Step 1, take the derivative. Step 2, set it equal to 0. Step 3, test your intervals if the derivative is positive, increasing, negative, decreasing. And so those are the main things you need to remember.